Any blockchain solution reaches its limits in terms of computational resources and overall capacity, and this is where scaling comes in. In this series, we'd like to explain more about sharding and compare sharding designs of other networks with the Everscale design, as sharding is a key and the only solution to solve the scalability problem. It would be fair to compare any sharding models in terms of what they actually shard. Sharding can be divided into three types: sharding of disk or storage resources, sharding of network resources, or sharding of computational resources. If we jump ahead a bit here, the first bottleneck that each network faces is computational resources, and Everscale solves this problem through its asynchronous model. In a nutshell, sharding means splitting the entire blockchain into n amounts of shards, or blockchains, that each stores and/or processes its own data. The Elrond network's implementation of sharding divides the blockchain state into shards held by subsets of nodes, where one subset stores one piece of data, while another subset stores another piece of data. If you divide a blockchain into n states, then n amount of parallel chains appear. All chains, shards, exist independently and store their own set of data. This is what's called data sharding. According to this approach, each shard has its own set of validators to produce blocks, and if shards need to pass a message to each other, there's a requirement to perform cross-change transactions, like Elrond does. How sharding works on Everscale? What is computational sharding? There's a set of validators, let's say 1,000, forming a work chain, or a data shard. Each block, for a processing shard, is produced in one round. One block is formed, or collated, once per second in each chain. After that, a total of 1.5 seconds is required to finalize the block, and after finalization, it is passed on to all validators, which broadcast all messages between each other. According to this process, the workload for each instance of processing is 0.5 megabytes every 2 seconds, which means that when using 1 gigabit network bandwidth, 200 processing shards can be in full synchronization. Full sync between all processing shards means that all chains communicate with each other and can verify any block that is produced by any shard. The validators don't need to perform any cross-chain transactions, as all messages are already written within each block. This means that the data between all validators of processing shards stays the same. We don't need to create parallel chains with sharded data, but computation takes place in a parallel way. Of course, when 200 processing shards isn't enough, you can always launch a new work chain, i.e. add 1,000 more validators. So what's the difference? Each chain or shard on Elrond lives by itself. It doesn't send any blocks to other chains. All of the data is different on all chains. These are parallel blockchains with a common mechanism to perform cross-chain communications. Meanwhile, each chain or shard on Everscale's workchain can see and verify all blocks from other chains. In producing a block, each chain receives messages from other chains. There is no need to send transactions to the master chain. All messages are already included in every block, and that's why all validators rotate, which gives us a completely different level of security. 1,000 plus validators to each work chain against Elrond's 10 to 20 validators per chain. This is a crucial difference. Basically, on Everscale, 1,000 validators share the same data between each other, but processing is divided between them. To sum up, Everscale is the only blockchain able to perform both computational and data sharding. Moreover, its unique design and approach allows us to solve the first bottleneck of blockchain scaling, which leads to top-level security, which is increased exponentially as the network scales. Please feel free to dive deeper into our technical documentation, and don't hesitate to ask any questions within the community. Stay tuned.